Hi, everybody. This is Mr. Folly, who's trying to dig his pen out of his computer. Success, success, success. And welcome to the last, oh no, podcast of, that's not what I want, the last podcast of Big Idea 1. So we're going to look at periodic trends. Oops. And, magnify that a bit. There we go. And let's see what color. Oops, I'm on the select tool. So, where's my draw? Actions, tools. There we go. I'm so sorry. This won't happen again. All right. So periodic trends. Periodic patterns. You know them, but don't explain them. This is what we're starting with. The atomic number is the number of protons, and it increases from left to right and top to bottom. So if you look at your periodic table, you'll see that this is 1, this is 2, this is 3, this is 4, this is 5. And as you go down, this is 1, this is 3, this is 11, this is 19. So that's it. The outer electron configurations repeat. So if you look at this closely, see how this is S1, 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 D3, 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 P5, 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 P5. So those repeat. Atomic number, I just did that one. Electron configurations determine chemical reactivity to an extent. So why do we care about this? Reactivity matters. So let me do this again. Okay. Ooh, says pen. So let me do this again. Remember, single electrons, form bonds. Okay. So there we go. Periodic table groups. So the stair step breaks apart metals on the left side. So these are my metals. These are my non-metals. And notice how this is also a non-metal. And these guys right here are called semi-metals. And they're also the exact same thing as metalloids. So groups are families and columns. And those are all the same thing. So, and they have wonderful names. So, alkaline metals, alkaline earth metals, carbon group, boron group, nitrogen group. No one calls this a chalcogen. It's the oxygen group, but I saw it. It was kind of fun. Halogens, noble gases, and you can see where these are. Transition metals and inner transition metals. I do want to make a point that these are inner, not inter. Inner means inside, inter means between. So that's that. Periodic trends are due to size and nuclear attraction always, okay? So periodic trends are due to Coulomb's law. Bond energy is Q1, Q2 over radius squares. Just want to remind you that these are charges, and this is the radius, which is size. Shielding also plays a role, but may not need to be explicitly stated. That means it doesn't need to be explicitly stated, okay? Shielding is when inner electrons block the attraction of the nucleus for the outer electrons. Shielding happens in electrons with many energy levels, which makes it weaker attraction due to size and blocking the attraction. So if you find somebody really attractive, it's homecoming where I live, and you see someone in there, ooh, look at that little honey, I find them very attractive, but their family is the scariest group of people you've ever seen. They're, I don't know, ready to attack you, and they're vampires or something like that. That would shield your attraction, and you'd be less attracted to a family full of vampires. All right, nuclear attraction is sometimes called Z. Z effective is the effective nuclear charge. The real charge is when you consider that this is the real charge, when you consider that shielding lessens the attraction. Okay, so let's look at some trends. Atomic radius, which is size. So notice it gets bigger as you go down. And it gets bigger as you go left. Okay, why? As you go down, every shell gets about 10 times bigger. So we're adding energy levels, okay? It increases as you go to the left. This is a surprise. As you go left, you have fewer attractive protons, so the pull on electrons is less. So if it's not as attractive, if your nucleus isn't very attractive, then the pull on the electrons is less. You often describe why it's smaller getting to the right. As you go to the right, the additional attractive protons pull in valence electrons a bit more, making the radius decrease slightly. Okay. Here is a graph of the periodicity, repeating trend of size. Small, big, big, big. Smaller, 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 big. Smaller, 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 big. Smaller, 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 big. And that's the repeating trend of it. So where are the big ones? Let's take a look again. The big ones are, the big ones are right here. Here's the biggest one. So notice how if I compare these two columns, see how the left column is bigger than the right column. Ionic radius, which is the size of the positive or negative ions. I'm going to say ignore this because it's so hard to see what it is. Positive ions are much smaller than their atoms. Positive ions lose electrons. Positive ions lose an energy level. So if I used to be this big and I lose this energy level, I'm now this big. Isn't that a lot smaller? So if my radius used to be 10, now it's 3. Okay. Negative ions are a bit bigger than their atoms. Negative ions gain electrons that repel other electrons. So electron-electron repulsion spreads it out so that the electron cloud gets a bit bigger. So if I'm this big and I add an electron, right? So if I add, let's say I have 3 electrons, and I add this one right here, see how this new electron would push this one out, and this one out, and this one out, and this one out, and my new size now is just a bit bigger, okay? All right, comparing ion sizes to atoms and other ions. So you count the protons and you count the electrons. All right, use the electrons to determine the shell of the particle. Lower shells are always bigger. 4s is lower than 3s, so 4s is bigger. If on the same shell, fewer protons is bigger because there's less attraction. All right, so let's take a look at ranking the following by size. O2 negative, neon, sodium, and Na positive. So oxygen has 8 protons. Now if it's O negative 2, 8 protons, 10 electrons. Neon has 10 protons, 10 electrons. Sodium, 11 protons, 11 electrons. And sodium positive, 11 protons. Notice how protons don't change. And 10 electrons. So the first thing I'm going to notice is that all of these, everything here, has the same number of, nope. So I've got 10 electrons, 10 electrons, 10 electrons. But over here, I have 11 electrons. So the 11 electrons, sodium, is on the 4th energy level. So let me see if I can sell you on that. Sodium is right here. That's on the 4th energy level. So it's the biggest. Everything else has 10 electrons, which means it's kind of based on neon, right? So if it's based on neon, then, I circled the wrong one for sodium. That's what I get for that. Here's sodium. Sodium's on the 4th. Well, I guess it's on the 3rd energy level, not the 2nd. My counting skills are poor today. So if I'm looking at neon and everything else has 10 electrons, then I simply rank them by, I rank them by which one has for size, the biggest. So I have Na, and then it's going to be the one with the fewest protons. 8 protons is the fewest, O negative 2. Next fewest protons is neon. Next fewest protons is Na positive. Remember how we already said Na is the biggest, okay? So that's it. All right. Electron affinity, the ability to attract free electrons. All right, so, I just unplugged myself. All right, so electron affinity increases going to the right Remember, we're trying to attract electrons because it has more attractive protons. Remember, protons are attractive, so they'll pull them in. Electron increase is going up because the size is much smaller due to fewer shells, which makes the attraction of the nucleus greater and makes it easier to attract free electrons. If you ever wanted to go out to eat somewhere and some place is close and some place is far, do you ever pick the one that's closer? I know I do. So just being closer makes you more attractive. So note to scoring points, and we'll go to this more. I need to talk about the size, I need to talk about attraction, and I need to address the trend. Electronegativity is essentially the same thing as electron affinity. Electronegativity is the ability to attract bonded electrons. And remember, electron affinity is attracting free electrons. So if you are attractive to married people, you're probably also attractive to single people. And that's the idea. And the trend is exactly the same. It increases as you go to the right because as you go to the right, you have more protons. And protons are more attractive, so the ability to attract electrons would increase. And as you go up, the size gets smaller. And if you're closer to something, you're more attractive to something, right? So if you see a little honey that you want to be more, though you want to be attracted to you, what should you do? Get closer to them or move farther away from them? It's get closer to them, okay? Again, size, attraction, restate the trend. All right, first ionization energy mentioned before. Energy to remove a valence electron from the gaseous atom. It increases going to the right because if it's smaller, has more attractive protons. Smaller, more attractive protons, size, attraction. So it takes more energy to remove a valence electron. It increases as you go up because it's smaller, fewer energy levels. Small size makes it more attractive. So it takes more energy to remove a valence electron. Do you see how every time we're talking about size, attraction, and then redefine the trend, more energy to remove a valence electron? All right, now comes the mean part. It's chemistry, so welcome to the world of exceptions. Exceptions in the ionization trend. Okay, so notice how it should be going up, restart, up, restart, up, restart, up. And it kind of does that, but we got a couple of little boo-boos in here, right? We got a boron, and we got an oxygen, we got an aluminum, we got a sulfur. Boron group is the first element in a higher energy p subshell. So see how this one right here? That's a higher energy p subshell. The higher energy shell is less attractive because it's farther away, so it's easier to remove the unstable electron. So that's far away. It's kind of like the outlier. It's way out there, easier to steal. Just a little bit easier to steal, right? Oxygen group. This is the first time you've got two of them in there. Remember we talked about, we used the bed analogy. Oh, AP Chemistry gets to go on a trip and there's 3 of you and 3 beds. Well, guess what? You're going to spread out, right? Now there's 4 of you and 3 beds. Little creepsters, right? That little creepster, someone says, do you want to go to a different room? Yes, I do. And you're going to leave quicker than the other ones, okay? So because electrons repel each other, putting a second electron in an orbital is less stable and easier to remove, so it takes a bit less energy to remove it. All right. Successive ionization energy in identifying a family. Look at this data. The second ionization means taking off the second electron. So first ionization energy is lose 1 electron. Second ionization energy is lose 2 electrons, lose 3 electrons, lose 4 electrons, okay? There's a huge jump for each element. This huge jump means you're leaving the small, attractive Ng is noble gas state. Okay, so 250, 500, 800, 3,500. That fourth one was leaving the noble gas state. So let's take a look at that. That means this was the fourth. This one right here was the third. By the way, it landed here. This was the second. This one was the first. So what we can do to note a pattern is huge minus 1 tells you the family. And then note only representative elements. Now, what's the representative element again? That's S and D blocks. Okay. So let's see if we can make this make sense on our other ones, okay? So that means this guy came from the boron group. Let's look at the next one. 600, that's about 700 more. That's about 6,000 more. See how I changed by a factor of 10? So that means my third energy level was huge. Huge minus 1 means it's going to be the second energy level. So let me change my color and see if I can make this make sense. So that means this group right here is called the alkaline earth metals. The first one would be small. Why is it small? It's not leaving a small, stable, noble gas. The next one would be small. Why is it small? It's not leaving a small, stable, noble gas. This third one would be huge. When you leave the small, attractive, noble gas state, that means that it takes a lot of energy to do it, right? I told you the opposite of a small, stable, noble gas state is Elkhart, Indiana, where I grew up. My brother, quite smart as well, his rule for college was the farthest away from Elkhart, Indiana he could go for free, okay? If you asked him why did he go to the University of Houston, the farthest school from Elkhart, Indiana that he could go for free. All right. Trends in reactivity. Ionic compounds and reactivity. So trends in reactivity. Metals. Metals lose electrons. Okay? Remember my metal line is right here. And that's my metal, non-metal line. So metals lose electrons. So the most reactive are the best losers. Isn't that weird? How do you become the best loser? You need to be big and unattractive. Where are you going to be the biggest? Down on the bottom. When are you going to be the least attractive? Fewest protons. Okay? Now I'm sure this is all written down right here. Metals lose electrons, so the bigger, less attractive metal is closer. The bigger and less attractive the metal is, the most reactive it will be. Most reactive metal on Earth is francium. Oh, look out, francium. Non-metals. You need to know non-metals gain electrons. If you gain electrons, you should be small and attractive. Now, I do want to point out that the noble gases are non-metals, but they don't react. So that means fluorine is the most reactive non-metal. Okay, so remember how things can be totally different. Like you could be the most attractive dog is different than the most attractive flower. Those would have different approaches for it. Okay, so non-metals gain electrons to react. So the smaller, more attractive a metal is, the more reactive it will be. As I go up, it is smaller because it has fewer shells. As I go right, it's more attractive. It has more attractive protons. I like to think of that like money. People can be more attractive if they have more money because then you have more opportunities to do what you want to do. Ionic compounds react by metals losing electrons, while nonmetals gain electrons. The number of electrons gained or lost is based on their valence electrons. Remember, we're always going to end up with 8, right? So if I've got 1, if I lose 1, I get to 8. Okay? Charge is determined by the number of valence electrons. So here's your charge again. +1, +2, +3, 0, -3, -2, -1, 0. And you absolutely need to know that. Okay? Charge is determined by the number of valence electrons, size and attraction, not the number 8. So never mention 8. Examples are Mg and Cl. Mg is right around here. Mg is +2. Cl is -1. Cl is right here in the -1 column. Okay? And then if I compared aluminum, which is right here, and bromine, which is around here, aluminum +3, bromine -1. So what happens there is, we'll get to the next one. And then P, which is -3. Phosphorus is right around here. And rubidium, which is somewhere around here, it's +1. So notice here, remember I talked about charge, right? So bond energy equals Q1, Q2 over radius squared. And remember, Q's matter more. And the reason why is because of like 200 or 300%. So see this right here, the Q product here would be 2. The Q product here would be 3. 3 times 1 is 1. The Q product here would be 3. Okay? So which one's stronger, aluminum and bromine Aluminum and bromine, I'll highlight this. Aluminum and bromine, I want to make sure I get it in the right spot. Now the third one. Third one down. So the fourth column. Aluminum and bromine, or phosphorus and rubidium. And rubidium is in the fifth row. 1, 2, 3, 4, 5. This is rubidium for real. Okay. So do you see how rubidium is much larger? So weaker, right? So my bond to my wife is strong because we're so close to each other. If my wife moved to Walla Walla, Washington, then my bond would be weaker and she would be stepping out on me and it would all be over and my life would be sad. Okay. So larger is weaker, bigger distance is weaker. So that means that AlBr3 is the strongest. I just misspelled strongest, but you get the idea. And that, I think, is it. That is it. And to that, I will say, toodles.